If you've ever looked up at the stars, you've wondered, how long would it actually take to get out there? We live on Earth, this pale blue dot, and we know we're spinning around the sun with 8 planets and a whole bunch of other stuff like moons and asteroids caught in our solar system. The solar system is huge, but it's only one of many in our own Milky Way galaxy, which has hundreds of billions of stars. When you think about that scale, traveling anywhere seems impossible. And yet we send probes and people out there all the time. But the real time it takes to get to Mars or Jupiter or even the nearest star is probably way longer than you think. And it has nothing to do with how fast our rockets can fly. It's all about when the universe lets us leave. Right now, our fastest crew capsule, the Orion spacecraft, tops out at about 20,000 miles per hour. That sounds fast, but even at that speed, reaching Alpha Centauri, the nearest star system, would take over 148,000 years. Even the fastest probes we've ever launched, like Voyager 1 and 2, which are moving at over 35,000 miles per hour, would still take 40,000 years just to travel 2 light years. Forget that. Forget centuries. Today we're finding out the real time it takes to reach every major stop on our celestial road trip, and what makes those trips so ridiculously long. First, you need to understand that the distance we measure in space is often a lie. It's not like driving a car where you take the shortest route. Getting to another planet is a game of planetary alignment. When Earth and Mars, for example, are on the same side of the Sun, that's when the launch window is open. If you miss that window, you have to wait months or even years for them to line up again. So when we talk about travel time, we're talking about the time it takes the universe to say, okay, you can leave now. Let's start with our neighbors, the inner planets, Mercury and Venus. Mercury, the speedy messenger. Mercury is the closest planet to the Sun, and it zips around quickly. It's a terrestrial planet, meaning it's rocky like Earth. Its craters are famously named after artists and writers. It orbits the Sun in just 88 Earth days. So, how long does it take to get there? We've sent a few probes. The Mariner 10 mission, launched in 1973, took over a year to reach Mercury, but it used a gravity assist from Venus to get there. The Messenger probe, launched in 2004, was the first mission to actually orbit Mercury. It launched in August 2004, but didn't actually enter orbit around Mercury until March 2011. That's a 6.5-year travel time, even though Mercury is one of the closest planets to us. The long travel time was necessary to slow the spacecraft down and line up its orbit perfectly so it wouldn't just fly past. Venus, the Inferno. Next we have Venus, the hottest planet in the solar system. It takes 225 Earth days for Venus to orbit the Sun. We've sent multiple missions, but one of the earliest successful flybys was Mariner 2, which launched in August 1962. It reached Venus in December of that same year. That's only about a 4-month trip. So we have a problem already. It took us over 6 years to reach Mercury, but only 4 months to reach Venus. Why the difference? Because getting to a planet is about efficiency and alignment. The longer trips aren't due to slow rockets. They are planned to use minimal fuel and perfect timing to put the brakes on when we get there. This is especially true for missions that need to slow down to orbit a planet, which takes precise, long-duration adjustments. Now let's talk about the most talked about destination, Mars. Mars, the red destination. Mars orbits the Sun in 1.9 Earth years. That's almost 2 Earth years for Mars to make a single loop. We've sent more missions to Mars than any other planet, so if we want to send people, we need the planets to be perfectly aligned for an efficient trip. These alignment windows occur every 26 months. If you miss that 2-year window, you have to wait another 26 months. So when the alignment is right, how fast can we get there? Typical travel time using current technology is about 6 to 9 months. For instance, the Curiosity rover, which launched in November 2011, took about 8 months to reach Mars. This travel time, however, is planned based on the speed of the launch window. We don't just fire and forget, we wait for the perfect moment. The most time-efficient path, called a Hohmann transfer orbit, minimizes fuel but requires a longer time. If we tried to go much faster, we'd burn way too much fuel, and we wouldn't have enough to land or slow down. So, the real time it takes to get to Mars? It's not 6 to 9 months, it's 26 months, plus the 6 to 9 months of travel, because if you want to leave, you have to wait for Mars to be ready for you. We've covered the rocky inner solar system. Now things get much bigger and much longer. We are talking about Jupiter, Saturn, Uranus and Neptune, the gas giants. They make up 99% of the mass of our solar system, not counting the Sun. Jupiter, the king of giants. Jupiter is the largest planet in the solar system, with more than double the mass of all other planets combined. It takes 11.9 Earth years for Jupiter to orbit the Sun. To reach Jupiter, we have to look at the workhorse probes that define deep space travel, Voyager and Pioneer. Pioneer 10, launched in March 1972, was the first to cross the asteroid belt and reach Jupiter. It reached Jupiter in December 1973. That's a trip of just under 2 years. The Juno probe, a more recent mission, launched in August 2011 and entered Jupiter's orbit in July 2016. That was a travel time of nearly 5 years. Why the difference? Again, trajectory. Juno used an Earth gravity assist maneuver, swinging back past Earth in 2013 to boost its speed toward Jupiter, making the overall journey longer but more fuel efficient. The travel time depends entirely on what the probe is designed to do: fly past or settle into orbit. Saturn, the ringmaster. Saturn, famous for its rings, has more moons than any other planet in the solar system. Its orbit takes 29.5 Earth years. The Pioneer 11 probe, launched in April 1973, was the first to reach Saturn. It used Jupiter's gravity as a slingshot after its flyby, dramatically increasing its speed and changing its course to reach Saturn in September 1979. That's a 6-year trip, even with Jupiter's help. The most celebrated mission to Saturn was Cassini-Huygens, a partnership mission launched in 1997. To reach Saturn, Cassini executed multiple planetary flybys: Venus, then Venus again, then Earth, and finally Jupiter, to gain the speed needed for the long trip. It arrived in July 2004. Total travel time for Cassini, almost 7 years. Now let's step into the truly distant and cold realm. Uranus, the ice giant. Uranus, an ice giant, has only been visited by a single spacecraft. It takes a staggering 84 Earth years for Uranus to complete one orbit around the Sun. The one and only probe to visit Uranus was Voyager 2. Launched in 1977, Voyager 2 had a meticulously planned trajectory to use the gravity of the massive planets it flew past to gain velocity for its next target. This is known as the Grand Tour trajectory. Voyager 2 reached Uranus in January 1986. That's a travel time of over 8 years. Neptune, the farthest frontier. Neptune, the outermost planet, takes 164.8 Earth years to complete its long orbit. It takes light over 4 hours just to travel from the Sun to Neptune. Voyager 2 continued its grand tour and reached Neptune in August 1989. That's a nearly 12-year trip from Earth to the furthest planet in our solar system. When Voyager 2 finished its mission, it became the only spacecraft to have visited Uranus and Neptune. Today, Voyager 1 and 2 are operating in the interstellar medium, that area outside the magnetic influence of our Sun, a huge protective bubble called the heliosphere. Voyager 1 took more than 30 years to cross the boundary of the heliosphere, which is about 11 billion miles from the Sun, to enter interstellar space. The lesson here is simple. Reaching the outer planets is less about pure speed and more about playing cosmic billiards. Those multi-year travel times are spent carefully swinging around inner planets to get a gravitational assist, turning them into massive, solar-powered slingshots. The universe doesn't care about a direct route, it cares about efficiency. Beyond the gas giants, we enter a different domain, the Kuiper Belt, home to Pluto and other dwarf planets. Pluto, the object formerly known as a planet, is a small, cold world of nitrogen ice. Pluto, the icy outlier. Pluto takes 248 Earth years to orbit the Sun. The New Horizons mission holds the record for the fastest trip to Pluto. Launched in January 2006, New Horizons screamed away from Earth, passing the Moon's orbit in just 9 hours. It reached Jupiter in 2007 for a gravity boost, and then spent the next 8 years coasting through the deep blackness, hibernating for most of the journey. New Horizons reached Pluto in July 2015. Total travel time was 9.5 years. Imagine the distances. Pluto's orbit is, on average, 39.5 astronomical units from the Sun. 1 AU is the distance from the Earth to the Sun. If we look at the whole picture, the Kuiper Belt is located between 30 and 50 AU from the Sun, and it is surrounded by the huge, theorized Oort cloud. This is like the cosmic deep freezer, full of comets and frozen stuff that occasionally loops into the inner solar system, giving us strange visitors. In 2017, we found one such visitor, Oumuamua. Oumuamua was the first interstellar object ever detected, meaning it came from another star. We found it was traveling on a hyperbolic trajectory too fast for the Sun's gravity to capture, moving at 87 kilometers per second. What's interesting is that when it passed the Sun, it accelerated instead of slowing down, suggesting that some force from inside the object was acting as a thruster. Another interstellar comet, 3I/Atlas, was spotted in 2023, coming in from an entirely different part of the galaxy, possibly from the thick disk, making it an unfathomably ancient object, maybe more than 7 billion years old. What's fascinating about 3I/Atlas is its planetary grand tour. It passed Mars, Venus, and then flew by Jupiter at 53 million kilometers. So if we want to reach a star system, like Alpha Centauri, those travel times become truly massive, tens of thousands of years. But we have an idea to speed things up, the Breakthrough Starshot project. The idea is to use tiny robotic probes called starships and fire them into space one at a time. These nanobots would ride the beams of a colossal, ground-based laser array. The goal is to accelerate the craft to a stunning 20% of the speed of light, over 130 million miles per hour. If this works, one of these little spacecraft could reach Alpha Centauri, which is about 4.37 light-years away, in just 22 years. However, because Alpha Centauri is still 23.5 trillion miles away, the signal carrying the data back to Earth would take 4 more years to arrive. But that changes the whole game. Instead of taking tens of thousands of years, we're talking about a human generation. The main obstacle is the amount of energy needed. The lasers would require 100 gigawatts of power, equal to the total US electricity usage, for 10 minutes. Let's pause and reflect. The reason we spend years of travel time on those long routes isn't because our rockets are slow. It's because every single deep space mission is designed to play the efficiency game, using planetary alignments and gravity boosts to save fuel, turning years into decades. Think about this. If we can reach another star system in 22 years, why does it take us months to reach Mars? The answer is mass and safety. The Starship vehicle, designed to carry people and 100 metric tons of cargo to Mars, has a huge size and mass, which needs a controlled, predictable trajectory. The focus is on reuse and self-sufficiency on Mars, which demands slower, calculated travel times. Let's talk about the destinations that are already in play: the International Space Station and the future missions to the Moon and Mars. The International Space Station, the ISS, orbits Earth in low Earth orbit, about 250 miles above the surface, which is inside the 1,200-mile limit, generally defining low Earth orbit. How long does it take to get there? Since the Space Shuttle retired in 2011, astronauts used Russian Soyuz capsules and now rely on commercial options like SpaceX's Crew Dragon. For Soyuz, the crew launches from the Baikonur Cosmodrome in Kazakhstan. A typical trip takes about 2 orbits or 3 hours to dock at the station. SpaceX Dragon missions follow a complex set of height-adjust maneuvers to match the station's orbit, which takes roughly 2 to 3 days. Dragon first achieves a preliminary orbit, then performs a series of firings of its 18 Draco thrusters to close the distance. The approach requires a series of strict go-no-go checks by mission control before it is permitted to enter the keep-out sphere, the 200-meter imaginary boundary around the station. The final step is capture by the station's robotic arm, the Canadarm2. The time it takes to get to the ISS varies wildly, from 3 hours to 3 days, based on the vehicle and the desired trajectory, but the ISS is constantly moving at 17,500 miles per hour, making one full orbit of Earth every 90 minutes. In a single day, the station completes 16 orbits, meaning the crew sees 16 sunrises and sunsets. Deep space, Artemis, and the Moon. NASA's current program to return humans to the Moon is Artemis. The goal is to establish a long-term human presence on the Moon. The Orion capsule, powered by the Heavy-Lift Space Launch System rocket, is the vehicle designed for this. Artemis IV, an uncrewed test flight, spent 10 days orbiting the Moon. Artemis II, the first crewed mission, is planned for 2026 and will perform a free return flyby of the Moon. How long does a Moon trip take? The mission to the Moon involves a 3-day journey to get there, a period of orbiting, and a return trip. The trip will only get shorter when we start using more advanced technology, like the Starship vehicle. Mars Sustained Presence. Returning to Mars, the 6 to 9 month trip, is just the beginning. The goal is no longer a flag-planting mission, but enabling a self-sustaining human presence on the planet. This means we need starships to deliver supplies, test infrastructure, and find resources like water ice. The trips are long, but the need for resources means that just like the ISS, we need to focus on recycling and sustainability to reduce our reliance on Earth. For example, 90% of water can be recycled on the ISS, a protocol that will be important for Mars. Water will be used not only for life support and growing food, but also through a process called electrolysis and Sabatier reactions to produce oxygen and methane propellant for the return trip to Earth. The biggest time challenge here isn't the outbound trip, it's the return trip. After landing on Mars, the Starship will be refilled with propellant produced on Mars using local resources before launching directly back to Earth. This process of gathering and producing fuel takes a huge amount of time, and the windows for Earth-Mars alignment must be perfectly hit. The true time commitment to explore deep space isn't just the few months it takes for the rocket ride, it's the years of planning, waiting for planetary alignments, and gathering the fuel and resources needed to come home. We've seen that travel times range from a few hours to the ISS, to over a decade to Neptune, to generations to the stars. The core reason those deep space trips take so long is simple physics. We can't go faster because of the speed of light. The speed of light, 300 million meters per second, is the absolute speed limit of the universe. Our probes are moving at a fraction of that speed. If we could travel at the speed of light, it would still take 4.37 years to reach Alpha Centauri. This concept of distance and speed is why astronomers use the light year, the distance light travels in a single year, to measure the vastness of space. But let's talk about the true barriers to fast travel, the ones that defy our everyday understanding of motion, gravity, and frame dragging, gravity and space-time. Einstein taught us that gravity isn't just a force pulling things down, it's the curve in space and time caused by the presence of matter. Matter tells space how to curve, and space tells matter how to move. A heavy object like a planet creates a dent in space. A ball thrown past it is just following the curve of the dent. If you compress matter into a black hole, an object so dense its escape velocity is greater than the speed of light, it creates an infinitely deep well in space-time. The faster you move near a massive object, the weirder space gets. Near a spinning black hole, there's an effect called frame dragging, where the black hole's rotation literally drags the space around it. Think about the time it takes to get to Mars. We calculate that based on classical Newtonian motion. But the closer we get to truly massive, strange objects, the more those long trips are complicated by warped space. The distance might be the same, but the space-time itself is distorted. The jet engine barrier. Even if we developed an amazing warp drive, there's an energy problem. The immense power needed to accelerate matter to near the speed of light is difficult to overcome. Astrophysical jets, like the ones shooting out of massive black holes in active galaxies, are the most powerful accelerators we know of. These jets, which are highly collimated streams of charged particles, often travel at speeds close to the speed of light. How do they get so fast? They harness the rotational energy of the central black hole and the magnetic fields created by the swirling accretion disk. The powerful magnetic field winds into a cone at the poles, funneling and accelerating charged particles from the disk into powerful jets. This magnetic energy extraction, called the Blandford-Zanajek process, shows us that energy can be extracted from a spinning black hole. However, the jets aren't made of material from inside the black hole's event horizon. the material is accelerated just outside it. These jets can extend millions of light years into space, dwarfing the size of the galaxy that produced them, yet they are still bound by the speed of light. They are the ultimate cosmic speed demons, but they only confirm the universal speed limit. So why can't we just build faster rockets and cut those decades-long trips to the outer solar system down to months? Because the faster you try to push mass, the more energy you need, and even the most efficient engines we can imagine, powered by nuclear fusion, are a joke compared to a black hole. Nuclear fusion, the process that powers the sun, converts about 0.1% of mass into energy. Accretion onto a black hole, however, is up to 40% efficient in converting gravitational energy into light and radiation. The sheer energy required to shave years off a trip makes it currently impossible. We are forced to wait for the planets to align, rely on those slow, looping gravity boosts, and accept the long travel times set by the cosmos. You've seen the real time it takes to travel across our solar system, and why those missions take years or even decades. It's about patience, alignment, and energy. We've learned that the short trip to Mars is only possible because of that 26-month launch window and the slow. But there is a next step in this story that we need to talk about. The biggest problem with the human journey to Mars isn't the 9-month flight. It's what happens when we get there. Mars may have water ice and the promise of self-sufficiency, but we need to ask, are we ready for it? For the rest of the story, click here to watch Mars is Ready, We Are Not, which details how Mars has all the resources we need, but humanity is still struggling with the physics and planning required to make permanent life there happen. Click here, and I'll see you there.